All right, so now we are going to look at one-to-one functions. So this lesson is given and is delivered after you have learned and have had enough experience with working with functions. And so I expect that when you arrive at this video lesson, you are already comfortable with working with function and any other and a lot of many other details of function. And so now we're going to investigate a property. So one-to-one function, one-to-one is actually a property. It's not just a function name. It's not a function name. It's just a property. So we're going to study those kind of functions where we regard to them as they are being one-to-one. Okay, so let's get into it. So now at this point, like what I said, expectedly that you have seen and a lot of my instructions about what functions are, and you have worked enough with the function and have built enough experience with function. Allow me to quickly bring up two little functions. How about for now, we're going to bring up functions that are represented as tables. Okay, so, and allow me to save all of those fancy wording. I'm going to come up with an f of x function. We're going to look at a g of x function. All right, so now f of x as a table. And in this lesson here, for simplicity, I'm going to just call the x variable here as the input variable, and the output is going to be the y variable. So on any of my table over here, the x is in one column, and the output is the y value, or just the output value of the function. Okay. And so for f of x, we have the following table representation. We have a 0, 1, 2, and 3. Okay? And it doesn't have to be fancy or lengthy or anything like that. Just one little nice example with two little functions. So here, how about all right, so these are the output values. Okay. And so now, for g of x, we have the following table. All right, so now, input and output. Okay, and then we can have 0, 1, 2, and how about 3? All right, so 1, 2, 4, 2. Okay, so those are the values. So these are just the rules of the function represented by the table, and this is just the rule for the function f. That's the rule for the function g represented by the table. So at this time, as I keep saying, as I've been saying, anyone learning in this video lesson should have learned and have worked enough with function and have built enough experience with function. So before I go on any further, allow me to bring up the following advisory here. So it is now at this point convenient to think of a function, to think of, say, on any function, f here or g here or any other function. Think of the way how the function works is that the function takes input to an output. Any function takes an input to an output. Any function takes an input to an output. So g takes an input to an output. F here takes an input to an output. So specifically, f here takes that input 0 and map it to and take that to the output 5. So the function f takes this input and bring that to output, takes that input 1 and come out with 4 over here. So a function takes an input to an output. This function takes that input to this output. This function takes this input 3 to that output 3. Okay, and so the same way over here, again, it's just for convenience. It's only a way to communicate between anyone doing math here, and a way to understand conveniently that this function g takes an input to an output. So specifically for this table, this function g takes this input 0 to output 1, takes this input 1 to output 2. This function takes this input 2 to output 4. Okay. And then this function takes this input 3 to input 2. And then, of course, all that rules about function are not supposed to be violated at all. So we won't violate as long as we have the function. And as long as I call any of these being a function, they have to satisfy that for each input is only taken to one output. Each input is taken to only one and to only one and uniquely one in output. Okay, so we've never violated any rules for the function. Okay, so now, but the next thing, and I haven't gotten into explaining what exactly a one-to-one function is yet, but now let's have a close observation here of this function, of these two functions actually. All right, so now I just grab a red marker and let me point out the following. Say for this input, think of that output 5 here. So f took 0 to 5, took this input 0 to 5. And so just like that, when we're going in that direction from the input taken to the output, it comes only to one output. Just like that, this input comes to one output. Okay, this input is taken to one output, and this input is taken to one output. Okay, and so nothing unusual with the way how we've been understanding about what a function is. But now let's look over to the other table over here. This function g takes this input 0 to the output 1. Okay, still that same rule. One input is taken to exactly one and only one output. Nothing violated. This function g takes that input to 1 and take that into output. Take this input 1 to output 2. So I gotta also clarify when I say it takes an input to an output, because through that process there was the rule that process. So the rule was behind the scene. The rule determined how this can be taken to that output. But then in the end, as a short story. So long story short, from inputs to outputs, this function g specifically took that input 1 and bring that to output 2 right there. Or just simply, for even shorter, this function g takes input 1 to output 2. Okay? And so now observe that. So it takes input 1 to output 2. It takes an input 2 to output 4. And it takes input 3 to output 2. Notice these are the same output. Same output. It's unlike this table over here. No output is repeated. As I just said, no output is repeated. And it's still, so but here, output is repeated. The output is repeated. But it's, now be careful and don't get me wrong here. I am not saying that one input is taken to two outputs. Nope, it's not the case. In any one of these inputs, each input here is only taken to one output. Clearly that's drawn by the chart here. But now I circle these two outputs. So now we particularly focus on the outputs. They are repeated outputs. So the idea now is that, now this function f, the rule is quite straightforward. Any one input goes to one output and no repeat on the output. But this function g here is the same rule, so it's still a function. It's just fine to be a function. Each one input gets taken to only one output. Each one input gets taken to one output. But now some output, like say, so really on this function g, the only outputs, or now at this point, I highly recommend this lesson is learned after you have learned what the domain and the range of a function is. So in another way of saying, once you have already understood what the range and domain of a function is, then the range of this function g, for this function g, the range is only, allow me to take quick notes here. The range is just only a limited set, being the value 1, 2, and 4 only. See, we have repeated outputs, but in the end, as far as just a list of outputs, we have only 3 limited output values. And so that means, as a further impact on this same outputs 2 right here, there were 2 inputs taken to the same output. There were more than one inputs taken to that same output. More than one input. See, there's input 1 and input 3 right here. Input x equals 1 and input x equals 3. More than one input gets taken to the same output. Whereas it's not the same case here. On any of these, on this function f of x, any of the outputs value, there was only one input came to that. Only one input came to that. Only one input came to this. Only one input taken to this output. Only one input taken to that output. But in this function, see, consequently, like I said, because we notice there's repeats. There's repeat in the outputs, so that means there were more than one inputs taken to the same output. More than one input taken to the same output. All right, so I just now distinguished, I made it clear, some function, on each output there was only exactly one input taken to that output. Say this is the case right here. On each output there was only one and exactly one input taken to that output. Only one input taken to that output. And I start saying that one taken to one taken to one. So this function right here, on each output here, there's only one input taken to that one output. Only one input taken to that one output. Whereas here, it's not the case. It's not the case. Some inputs got more than one. Some inputs got not only one input. So maybe I have accidentally said something wrong, but on some outputs got not only one input taken to it. For example, this output 2 right here, output value 2. There were more than one. There were not only one input taken to that output. All right, so ladies and gentlemen, this is the idea of what one-to-one function means. This function here, I would say, this function here is where I call that one-to-one. You see? Because in that understanding, in that convenience I was pointing out earlier, let's understand the whole idea. Long story short, a function takes an input to an output. So one-to-one here refers to that property of a function where for any output, there was only one and exactly one input taken to it. Whereas here, this function g, so f, so now allow me to write that a little more formally. So now I'm saying f, okay, is, and yes, I just erased that term and now I'm rewriting it again. F is one-to-one. See, this is the output, this is the input. That's kind of like the way how you can understand that. I mean, there's so many ways to interpret that. But the idea, now see, in the way how I want my students to understand this one here, because on any one output that you're looking at, there is one input taken to it. Only one and uniquely one input taken to it. Oh. On that one output, there was only one unique input taken to it. That's why this function f here, the way how this table is, it's one-to-one. Whereas this function g right here, now I can say g is not, okay, g is not one-to-one. All right, g is not one-to-one. All right, g itself is not one-to-one because see so some input, on some outputs, yes, it came out from exactly one input, just like that. This output, for this output, there was exactly one input taken to it. Okay, but for this output 2 right here, there were not only one input taken to that one output like that. That's why this function here fails to be one-to-one, or in other words, g of x here, this table is not a one-to-one function. All right, so now we're starting to have that idea in mind what exactly a one-to-one function is. Okay, so now let's navigate to my other board and derive a formal definition of what it means by being a one-to-one function. So now, in order to maximize my board space over there, I'm going to just rewrite these. Okay, so g of x is here. Okay, we know it's not one-to-one. Okay, and clearly the range for this 1, 2, and 4. Only those values. So we had repeats. right? So, or another way of saying we had repeats in the way how this table is constructed. We got repeated output values. Okay, that's another way of seeing that. Okay, so now let's come to a definition, a formal definition of what it means by being a one-to-one function. And so at this point, just like how I explained, being one-to-one, see, it's a being, it's an adjective, it's a property of a function. So any function, now at this point you have seen a lot, and I highly recommend viewing this lesson as well after you have learned all of your about your toolkit functions. So any of the functions that you have seen earlier, especially the toolkit functions, some of those are one-to-one, some of those are not. Okay, and so now let's come to a precise definition of what it means by being one-to-one. And so again, importantly to understand, one-to-one is a property, it's an adjective, okay, of a function. Okay, so a function f of x, okay, is said to be, all right, and allow me to write this term in red ink. The function f of x is said to be one-to-one. Okay. If, allow me to use past tense, if there was exactly one input, okay, exactly one input taken to each output. There's exactly one input taken to each output. So it's a property. It's a property in that way it is. So in the way how I just now explained, let's one more time swing back at my other board. Okay, so this function is one-to-one. Well, the good thing for us is it's a table, it's a function that's represented by a table. And so it's short and we can easily search through. So on each output, see, on each output there was, on that output, there was exactly one input taken to that output. On this output, there was exactly one input taken to that output. On that output, that's why I said on each output there was exactly one input taken to each the output right there. And so now see, on each of these outputs right here, there was exactly one input taken to that. That's why this function f is one-to-one. Okay. This function g, on the other hand, is not. Yes, maybe there was some outputs. Maybe some outputs had exactly one input taken to it. I agree. This is the case right here. For this output, there was exactly one input. For this output 4, there was exactly one input taken to it. But now for this output 2, you see the repeat in the table. See, the range of this function is only 1, 2, and 4. So for this output value right here, for this output value, there were not only one input taken to that. And this is the reason why this function fails to be a one-to-one. Okay? And so what matters for us now, in this way of defining it, it's a property. So what matters now is that whether a function is one-to-one or not one-to-one. Okay, whether it's one-to-one or not one-to-one. We don't particularly have a term for a function that's not one-to-one, but so we already define that term being a one-to-one. Anytime our function satisfies this requirement, okay, there was exactly one input taken to each output. As long as we satisfy that requirement, our function is a one-to-one function. It's a definition. And then as long as we recognize our function fails to be one-to-one, we just simply say, hey, the function is not one-to-one. Okay? And so in that work I was showing throughout the demonstration example, it's a property where sadly we have to really detect through, because like I said, in the definition, on each input, for each input, there was exactly, for each output, there was exactly one input taken to it. Okay, and so in order to satisfy what's stated in the definition, we have to check through the entire range. This function f here, I could have also mentioned the range of this. I should have done that as well. So f here has the range for f. I was short of space, so I was a little hesitating to write it down. 1, 3, 4, and 5. That's the set of the range. Okay, that's the range for this function f. So in order to decide whether this function here is one-to-one, and really the work I was showing that the whole time throughout what I was discussing earlier, I did check through every output into the range of this function to ensure that on each output that I checked, that I looked at, there was only one input taken to that. So we have to check. So in order to say that, hey, a function is satisfying this property, we have to check through every output to make sure there was only one input taken to that specific output. And so now when it comes to failing to be one-to-one, when it comes to failing being one-to-one, then as long as we meet one output that fails the requirement, this one output right here, y equals 2, it had more than one, there were more than one inputs taken to that. And so in that way, this function here, as long as we found that, we're going to just say, hey, this function g is not one-to-one. But in order to entirely say it's one-to-one, you got to check through every output value from the range. Okay? And I just now realized my writing is a little too squeezy here. All right. So range, just a note. 1, 3, 4, 5. Okay, that's the range for this function. That's the range for this function g. All right, and so now at this point, let's get ready for looking at some example. So there are going to be, the story is going to be, this concept of being a one-to-one function is actually a big concept. It's not small. It's going to lead into many other important topics in your later topics in this class, and also in your more advanced courses. But at our level here, allow me to minimize the amount of details like that, so that anyone learning from this only need to focus on this fact that as long as every output, okay, came from exactly one input. See, that's another way of saying that as long as any outputs came from exactly one input, that one is good to go for being a one function. Otherwise, if you have found any one output here came from more than one input, because see, a function takes an input to an output. That's why I had to introduce that convenient way of understanding it. And so now, as long as we recognize an output that came from more than one input, that function fails to be one-to-one. All right. So now we're good for erasing this part of the board, and then I can start firing up some example over here. All right. So to stay real close with the demonstration I have explained right there. Okay, to stay real close with the demonstration I have explained right there. Let's start out with example 1 here, simply by working with functions that are represented through tables. Okay, that are already represented by table. So example 1. Okay. Let f of x be represented by the following table. Okay, so I will be giving out a few different tables. Each table is a representation for a function. That's why I'm introducing with this instructed wording right here. This instruction wording right here. So let f of x be represented by the following table, and you're going to have part A with a table, part B with a table. Okay, and then we want to, so once we have the table given, we want to determine determine if f of x is 1 to 1. All right, that's all we have to decide. So that's all we have to decide right there. All right, so now in this case, here we go. Part A of the example. All right, so this is f of x. Okay, here's my x column, my y column, and let's stay in that convention that x is the input. That's familiar convention worldwide. X is the input and y is the output. Okay, even though we can be more flexible than that already. And then let's look at negative 1, 0, 1, 2, okay, and 3. How's that? Okay, all right. And so now the y value we can come out being negative 2, 1, 4, 2, 3. Okay. So these are my output values. So again, think of a function at this point, think of a function in a way that it takes an input to an output. It takes an input to an output. So that way of thinking will save, will keep your work in terms of deciding if a function is 1 to 1 or not. It will keep your work to run smoothly. Okay, so f takes an input to an output, taking an input to an output. So now in order to decide, because that's what we need to do, we need to decide whether this table representing our function f here appears to be a 1-to-1 function or not. We need to decide that. So 1 to 1 or not, we have to search through every output. The good thing is the range of our function here is short. Okay, we have a small range. The range of our function. See, so it's good habit to write down the range from a table like this. So these are the values here. Well, lowest is negative 2. That's the lowest for the range. And then I have 1, 2, 3, 4. Okay, it's just my choice to put these range out or these output values in increasing order, but that's not really a must. Okay, so we got the range. That means it contains all of the possible output values right from our function defined here. Okay, so now when we're looking at y value equals negative 2, ask yourself this question: Did this value, this output value, come from exactly one input? Did that output come from exactly one input? Yes, it is. Yes, it did. But then that doesn't mean we stop and saying the function is 1 to 1. Then now, did this output come from one and exactly one input? Yes, it did. That made two of them. That made these two outputs satisfy the requirement. But that's not all the outputs we search through. So we have to detect through every value, every output value of from our range of this function. So did this output come out from exactly one input? Yes, it did. So I should have drawn arrows as well. There was only one input. Taking to that, there was exactly one input, 0. Taking to that output. Okay, there was exactly one input. Taking to that output. There was exactly one input. Taking to that output. Okay, and there was exactly one input. Taking to that output. So the arrows are going parallel. On each arrow here, there was only one unique input right here. That's another way of seeing it. Okay, so for each output, there was exactly one and only one input taken to it. All right, and so now that's all we have. Once you're seeing that, okay, and we can throw in a conclusion of what we observed through the table. So I can just say, so here I'm firm that each output, this is another way of saying it, each output came from, okay, exactly one input. Okay, that's one way of saying that. That's one way of making your observation or stating your observation. Or somebody else can say, you know, there was, okay, because see, we have to take some inputs to an output to allow me to use a lot of past tense here. So there was exactly one input, okay, taken to each output. Okay, I'm just pointing out a few different ways how you can state your overall observation here. But when you're actually doing this and give your reasoning, I mean, you don't have to write all of these I'm writing down here. You are mature enough to understand what I mean. This is just how you document your thoughts right here. Okay, and just these are equivalent. So you only need to write one of the two, and you can even word in your own way as well. But now after seeing this observation, right, after stating this observation, now we come to our conclusion. All right, so now allow me to erase so that I can make space now. So f of x in this case is 1-to-1. Okay, so this kind of problem, I'm writing that in words. I showed the thought process. I stated the conclusion. Usually when it comes to the practical situation, when any of my students is doing the assignments, and for public viewers out there, if you have come to this lesson, be aware that when you're learning from your instructors, there will be the kind of problem where, and in these days, these kind of problems are a lot of times being put on the web as a web-based problem, as an electronic version right there. So usually it happens to the kind of, it happens in a way that it gives you a table from the web and say, hey, here you go, just quickly put a check if this function is a one-to-one function. So I made a lot of reasonings and statements, but in the end, these are meant for, you know, short answers, exercising problems when you are doing your actual assignments with your professors that whoever you're learning with. Okay, so you may be assigned to simply, here you go, in this problem you got a table. Decide if this table, put a check next to the table, for example. Okay, if this table represents a one-to-one function. Okay, so be aware about those kind of problems. Because in these days, a lot of mathematical assignments, a lot of math assignments are assigned on the web right there. It's just the way how the world is moving. I like it that way actually. Okay, it's quite convenient for some of those kind of problems that just require short answers. So in this problem right here, yes, I made everything in stated words, but you can, once you make your decision, you can just put a check. All right, now that's enough talking. Let's move on to part B right here. So again, remember, most importantly, the idea is in order to say one-to-one, in order to say you met that property, you got to check through every output to ensure it's satisfied there was only one input taken to that output. All right, now we are ready for part B. All right, so now let's look at part B, and I'm going to give another table. So this table is another table that represents a different function f of x. So here, how about, let's look at the inputs here and the outputs here. -1, 0, 1, 2. All right. We don't need to know what rules takes this input to that output, what rule takes this input to that output, what rule takes this input to that output. That's not important. That's not what we need to know. Okay? But the function here, in this function here, right here in this table, and like I said again, whatever rule that is, if you recognize it, that's good. Hold it to yourself. Okay? Whatever we see is right here in this table. These are the outputs, okay? The range include these values right here. 1, and we got to repeat, all right? I mean, so 0, that's 1, 4, 9. All right, so we know there's some repeat in the table. Okay, so is this table one-to-one or not one-to-one? You probably have an answer already by now, but allow me to show my thought process again. we got to check for every value. So on this input that we saw in our table first, on this input, okay, did that come from exactly one, I mean for this output, did that come from exactly one input? Well, for here it came from -1, but I mentioned about the repeats earlier. That same output there also came from inputs being +1. So in other words, on this problem right here, and we don't have to search on the other ones. Okay, if it happens immediately right on our first shot right here that we looked at one input, we looked at one output and we found there was one input coming to it, and we saw the same outputs there again, but that came out from a different input, right here, like in this case. Then we can start disregarding the other ones. Okay, so now I can see that y equals 1. This particular output right here came from. Okay, that's one way of making my observation, of stating my observation. So that's one way. Y equal 1 came from two different inputs. Okay, those are namely x equals -1 and x equals 1. And that's enough. Okay, that's one way of saying it, or another way of stating it, generally speaking. Okay. There were two inputs, okay, taken to y equals 1. Y equals 1 is an output. There were two inputs, more than one inputs taken to y equals 1. And like I said, this is just a way we're documenting our thoughts right there, our general observation. Okay, and so in that way now we have a firm decision. This function f of x here, okay, it's not 1-to-1. This function is not 1-to-1. It fails right there. It fails to be 1-to-1. All right, so that's how we're doing that. That's how we approach. And like I said, it can be a very fast process. I have to, in front of anyone viewing the lesson, I have to explain with a lot of details. So it seems like forever, but once you get yourself engaged into the structural steps here, then it's going to go a lot faster. Okay, let me bring up an FYT for anyone to try. So, assuming that you have seen quite a few lectures from me prior to this lesson, then you have understood what an FYT is. It's a problem where I wrote on the board here, but I won't show my own thought process anymore. Once you have all your freedom to pause the video and get yourself working on the FYT, and then once you resume the FYT, you can just simply see the final answer, okay, without any of my explanations. So now as an FYT, I want students of mine, I want viewer to decide if the following table gives us a 1-to-1 function. Okay. All right, so there's our table. Go ahead and pause the video. Work out your thought process right there. And if you're fast, that's good for you. If you're not, lay down the steps and write down your observations carefully. And then resume the video to see my final answer. That's all. All right, so now assuming you have already spent some time thinking through the problem. This table over here represented a 1-to-1. It is 1-to-1. It's a 1-to-1 function. Okay, f of x is 1-to-1. That's how we're saying it. And then there were time of just show my student to put a check there. As it's a problem that we're checking if it's a 1-to-1 function or not. All right. All right, so I started out the idea of being a 1-to-1 function through a table explanation, as an explanation through the table. And then we came to the definition. A function is 1-to-1 is said to be 1-to-1 if there was exactly one input taken to each output. Okay. Now, and the first example I've done there, we saw things we worked through with the table. Okay, but table is only one among the different ways to represent a function. So what happens if we have a graph? What happens if we are given a graph? Okay, so f of x, there's a function f of x here and a function g of x. This time, instead of providing a table representation of these functions, I'm going to provide a graphical representation. So what about f of x is represented by a graph like this? Okay, and g of x is represented by a graph like this. Okay, it's a graph. Any of these are graphs, and they all pass. Each one of these passes the requirement for being a graph of a function. Needless to say, and I don't even need to swing over to decimals yet. You see, we use vertical line test that you have learned, okay, to ensure that any one of these two graphs is the graph of a function. And needless to say, I brought these up because I intended that they are graphs of correspondingly f and g. So vertical line test is used to decide if the graph given here is the graph of a function g. Yes, they all pass the vertical line test. But now we want to know, is any of these functions 1-to-1 or all of them, or 1-to-1, or is some of them, or not one, is any of them not 1-to-1? Okay, we want to know if the function is 1-to-1. Okay, so recall for yourself again. A function is said to be 1-to-1. Is said to be 1-to-1 if there was exactly one input taken to each output. Only exactly one input to each output. Okay? And now as we are going along here, I have to point out another high recommendation. Again, I highly recommend that you're learning this lesson after you have seen my earlier discussions on what function is, particularly that lecture when I talked about any function has a graphical representation. Okay? Because here, in the way how I explain to my students, we always use, it's just a worldwide convention, a worldwide tradition. We use the horizontal axis to put the inputs. So this is inputs, the horizontal axis lists the inputs. That's where all of these x values are. If we consider the inputs as the x variable, and so the y variable, if we stay with the y variable as the outputs, then the outputs are being on the vertical axis. And so now blending that understanding into my definition, into the definition we've had there, then we want to ensure each output. So to clearly indicate each output, we got to draw a horizontal line, because a horizontal line goes through vertically right through each vertical height like that. You see? So it's a vertical height. It's a vertical height. That's why we use a horizontal line. So now on any horizontal line is in the line y equals a value, L for example. But see, that's a vertical height. Or in another way of understanding it, it's an output. So if for this output being L for example, are we having one input? So now I'm searching. I'm going to draw a horizontal line. And now I'm searching, hey, when that horizontal line crosses with my graph, is that at only one x values? Or when I draw a horizontal line and where my graph crosses, where the horizontal line crosses my graph, there were two inputs. Okay, See, in here for this graph in G right here, drawing this one horizontal line, and this drawing is just came out of a random selection. I randomly drew that horizontal line and representing an output, And then with this specific output right here, there were 2 inputs, because see, the horizontal line crosses my graph at 2 points. We're seeing it visually. So there were 2 inputs taken to that output. See, at this, in the way how this function g of x is, then g of x1 comes to that output y. G of x2 also comes to that y value, same y value. Whereas here I drew a line, it only crossed my graph at once. There was only one and uniquely one input for that. But then that's not satisfaction, and that's not satisfying enough. I have to draw another line. And was there just one x value? Yes, there was. I drew another horizontal line. Okay. When it crosses the x, when it crosses with the graph right here, was there only one x value? Yes, there was only one x value. Okay. So, ladies and gentlemen, anytime your function is given as a graph, as a graphical representation like this right here, I introduce for you this technique that's called the horizontal line test. Okay, that's what I just did. It's called a horizontal line test. Okay, so the whole idea here is that, so we use the horizontal line test for 1-to-1. It's another shorthand writing of that, for 1-to-1 function. Okay, for 1-to-1 function. Horizontal line test for 1-to-1 function. Okay, so what exactly does this do? If a horizontal line, because that's represent one output. Okay, like I said, this is any horizontal line. It's the way it is. Any horizontal line is placed at a vertical height, and that vertical height is tentatively our output of the function. Okay, and so if the horizontal line here crossing the graph at one point, and then at least it's indicating it had only one input. That output came from one input. But if the horizontal line crosses the graph at more than 1 point, okay, then that means it's not 1-to-1. The function fails to be 1-to-1. The function fails to be 1-to-1. And so the whole idea now is that we use a horizontal line test. The statement formally says if a horizontal line crosses the graph at more than 1 point, all right, if any horizontal line crosses the graph of the function at more than 1 point, okay, then the function, now we can say, make our conclusion, the function is not 1-to-1, or fails to be 1-to-1. It's not 1-to-1. All right, allow me to use a 1-to-1 with 1:1. It's another way of writing 1-to-1. All right, that's the whole idea of doing a horizontal line test. All right, so now allow me, it's just me, instead of sticking with the hand sketch, I would like to just use a machine right here to indicate. Okay, so now I'm going to come up to example 2 right here. Okay, and then we're going to look through that and look through the graphs this time. So I have left this definition here long enough. So now let me erase that and make space for my example 2. So I'm going to say let f of x be represented. Okay, let f of x be represented by the given graph. Okay, so that means I am going to walk you through, I am going to deliver part A, part B, and part C. So anyone learning with me, you have seen my style enough that any example itself where I put a number, example 1, example 2, is more like a class of problems. Okay, and then in there it's an opportunity for me to show as many problems of a similar kind in one example. Okay, so now let f of x be represented by the given graph. Okay, and we want to determine if f of x is 1 to 1. All right, nice and short. So now I am going to bring up the graph. So I highly recommend to use use graph paper in case you're taking notes along with this lesson right here. Then you can have graph paper and try your best to replicate the graph, to duplicate the graph. Or you can also take a photo shot of the graph. I will also put that on the screen as well. Okay, first I'll put it on full screen view, and then I'll put it on a little corner of the screen. Okay, so now here's our first graph, and this is the graph of the function f of x. Now keep in mind again, the point is we don't need to know what rule of the function. Is that an x squared? Is that an 1 over x? Is it 2x squares? Anything like that? We don't need to know the rule. We don't need to know what rule gave these graphs. Okay, we're only looking at the graphs and decide. So this is the graph for part A. This graph represents some function f of x, and I'm writing that in red ink right here. All right, so hopefully you have had enough time to take a photo shot or to copy it down to your notes. Now I am going to put that to a corner of my board. So this is the graph for part A, for our function f of x in part A. We're going to just simply use that to decide whether this function here is a 1-to-1 function or not. So again, recall yourself. As long as, in order to be 1-to-1, every output, there was exactly one input taken to each output. Okay, or another way of saying, on every output there was only one and exactly one input taken to it. Okay, and because of that, we came up with the horizontal line. We came up with the horizontal line test technique right here. We want to use that horizontal line, okay, and detect. So now on this graph right here, here's my horizontal line. Right now the horizontal line doesn't even cross because it's outside of the range of our function. Okay, and so now I'm going to bring the line up. So right here is where the line starts interfering with the graph, and that's, you can, in your experience with domain and range right here, then this is where we begin the range of this particular function. It starts with the with y equals 0, as low as y equals 0, and now right now the graph crosses at only one point, but that's not enough. But that's not enough to say it's 1-to-1, because once we recognize it's 1-to-1, we have to keep detecting at other outputs right there. And so now this is what I mean why we have to detecting at other outputs. We're going to move our horizontal line up and down right here. Okay, and see now, so now with the advance of with our advanced technologies in these days, we can easily move the horizontal line up and down, and now anywhere we're observing the line is going, anywhere we're observing that horizontal line is going, the line is only crossing our graph at one point, and so it's still meeting with the requirement so far. Okay, and then for now the graph kind of stops there. Okay, whatever graph that is. That's why I said earlier, nobody has to worry about what rule gives this, but at least the graph stops right here. So this is this height right here is about the end point of our the end of our range of the function. So when it comes to there, okay, then the horizontal line does not any longer cross with the graph, and so in that way, nowhere within this range, the horizontal line crosses the graph at more than 1 point, nowhere. And so now in that way, now I can make that firm decision. Okay, and let me still keep the graph here. So now once we have seen the behavior of that horizontal line, and we bring it up and down right there, and then anywhere we brought it up and down, it only crossed at 1 point. So now we have a firm decision. Okay, f of x is a 1-to-1. That's simple. F of x is 1-to-1, simply because this is the reason. See, anywhere a horizontal line is placed, okay, it crossed the graph, okay, at only 1 point. That's enough to make our statement. Okay, and again, usually with this kind of problem, because I want to show a lot of explanation and reasonings, that's why I'm writing that in words. Okay, but usually a problem like this kind, even though we switch to investigating graphs, but in the end, this kind of problem in these modern days likely will be assigned as web-based problems where your instructor, it could be me, it could be any other professors teaching the course, it could be assigning you a problem on the web, say, you know, that's ran through a commercial, either a commercial website that runs math problems, or a free website resource, the certified website resource that runs the math problems for students to use as exercises. Then these problems right here in these modern day belong to those fast online problems where you can just see, hey, they give you 4 or 5 graphs, okay, and then you quickly look at the graphs and use the up and down and horizontal line like that to determine and put a check there. If it's a 1-to-1, you put a check. If it's a 1-to-1, put a check. If it's not a 1-to-1, if it fails being 1-to-1, because at some point you can place a line and it crosses through at multiple points, okay, then you're gonna say then you skip the check there. Okay, so this problem here, on paper and pencil, I have to write down I have to document the thoughts right there, the thought process. But like I said, once you're fluent enough, you can just quickly put a check if you have decided if it's a 1-to-1 function or not. Okay, let's now move on to part B right here. And so here we are looking at another graph. Let's now look at part B, and let's look at the graph for part B right here. This, ladies and gentlemen, this is the graph for part B. And so again, for anyone who's learning along with this video lesson, I highly recommend that you can just pause the video to have a duplication of this graph right on your note right there, to copy this graph to your note. All right, pause the video. Feel free to pause the video if you feel you have to. All right, and now let's get to work. So this function, we want to see if it's we want to see if it's a 1-to-1 function or not. So the only way we're doing that, the only way that get us successful, place a horizontal line there. Okay, and so now, again, I have to mention, as long as we recognize there is a horizontal line that crosses the graph at more than 1 point, we're good to go. Stop right there and say the function is not 1-to-1. The function fails to be 1-to-1. So now with the graph here, I'm going to put in my horizontal line. All right, so horizontal line are here. Okay, so at least I see that the range for this graph goes from, now let me put it in some closer zoom right here, but the range of this graph starts down as low as -2 and going all the way up. So that's why now I'm going to start letting the horizontal line interfere with the graph, the region of the graph right here. Because right now the horizontal line is not crossing. Okay, and so now I'm going to use the horizontal line to bring it up. So now I already recognize there's a spot here, there's a height here, there's a horizontal line that crosses, there's this horizontal line that crosses the graph at 2 particular value. Okay, right there. Well, Desmos, this graphing utility is nice that it gives out the coordinates, but you can believe in your own eyes that whatever you're seeing there is the truth. This horizontal line I already found. Boom, one horizontal line. It already crossed the graph at 2 points. Okay, so in this case here, now we are ready to make our final conclusion. All right, so So now allow me to write down the reasoning first, okay? But like I said, be ready that the kind of problem you're doing here is more likely just they give you a graph and you put a check if it's a 1-to-1, and you skip the check, you clear the check if it's not 1-to-1. That's all there is, and then you hold on to the reasoning to yourself, okay? So I noticed that this horizontal line, and I mean the one you've seen in the picture, this horizontal line, okay, crossed the graph at, all right, more than one point. All right, that's fair enough. This horizontal line we're seeing here crossed the graph at more than 1 point, and that's just enough to say that. So in this case, our decision, my decision is f of x is not 1-to-1. All right, f of x is not 1-to-1. All right, it's just not 1-to-1. That's how we're doing it. Okay, and so now allow me to produce an FYT. All right, so with this function right here, I want my viewers, my students who are learning this with me, to look at this graph independently, okay, and then decide to yourself whether it's a 1-to-1 or not 1-to-1, and feel free to pause the video to make your thought process, to follow your thought process, and once you resume the video, I'll just tell you my own decision, okay, on the same graph that you're seeing with me. All right, so here it goes. Let me prepare the graph here. All right, so here we go. This is the graph for whatever function that is. This is the graph that represents our function f of x. All right, and now you can go ahead and pause the video to decide for your own whether this graph is whether this function given by this graph right here is a 1-to-1 function or not. All right, so now assuming that you have spent enough time and pause the video, now resuming with this video right here, now I can just tell you my decision. This graph to me, f of x represented by this graph, is not 1-to-1. Okay, this function here is not 1-to-1. All right. All right, so now we are ready for the third example, another class of problems here. So this time, I would like to introduce functions where they come with a known rules right here, like say f of x equals x squared, f of x equals absolute value of x, or f of x equals 1 over the 3 to the x, something like that. Okay, so let's look at the third example. So we want to, and I'm just getting straight into that. This one worded instruction: determine if the given f of x, if the given function f of x is 1-to-1, and allow me to explain all of my reasoning through the example as well, okay, rather than just talk a little bit about it before we got into doing it, because now you've had all that details. All right, so now part A, and this is what I mean right here. The kind of function you have now is going to be given, and you see the rules specifically written down. Okay, so f of x here equals, and so now x to the fourth minus 4x cubed. Okay, x to the fourth minus 4x cubed. The function itself, I'm not saying that it's among the function that that's known to you, okay? But here's the thing. You only need to see this rule, this function here as a rule. The rule says for each input, it's raise the input to the fourth power and subtract 4 times the cubic of that input. So that's the rule of this function applying to each input. But how are we going to decide if this function is a one-to-one or not? Because remember, the idea that according to the definition for being a one-to-one function, we want to ensure that there was exactly, or there is exactly, because we haven't done this one yet. So now I'm saying there is. We want to ensure there is only one and exactly one input for each output. Okay? But how can we do that? So when you advance to a higher course, you will learn even more solid technique to decide that algebraically with the math, okay, with the paper and pencil technique, they're very convenient, okay. But here, the best we can do is to use a graphing technology, to use a graphing utility. You can stick with the standard TI calculator that are widely used in many classrooms, okay, on standard, worldwide standard, or you can stay with the Desmos utility that I've been using right here. Okay, so my only advice when we come to these kind of problems where your function is specifically given, use a graphing utility. And my idea now is that we want to explain this completely graphical as an approach. Okay, I'm gonna show that technique right here. We want to prove it's one-to-one or not one-to-one completely by using the graphical approach. Meaning I'm about to use the horizontal line test. Once we saw the graph. Okay. So now, with my empty graphing space right here, and indeed, this time allow me to show full screen of the graphing utility right here, so that anyone, in case you decided to use Desmos, you will know again how to navigate around with graphing any given function. So how about something like this when you are in Desmos right here? So this left-hand side command entry right here is where you can input your function. So now I would like to click on that and type in my function. And it was f of x. I'll just type f in parentheses x. Okay, and I hit equals. Now let's just type in the formula for our function. It's x to the fourth minus 4x cubed. Okay, and so on standard with any graphing technology or with any technology to type math, raising power is we're gonna use that caret sign right there. We're gonna use that hat sign. So now on my graph, I'm gonna type x, and then, but that didn't come. So on my graph, I'm gonna type. So on my graph, I'm gonna type x. Okay. But that's not the complete function. So now I'm going to type raise power by doing the hat key. Okay, fourth power. But this is not the complete function. Now I'm going to exit out of graphing of superscript mode. I'm going to type a minus. Okay, and then 4x. But that's not our function. It needs to be 4x cubed. So right after that, where my mouse is blinking, where my cursor is blinking, I'm going to type the hat key. That raised me to a superscript mode. Now third power. That's the graph right there. That's the graph of our function. Okay, so now we don't even have to worry about seeing the complete graph in this limited window view. That's not important. Okay, but now with Desmos, you can also do the following. I mean, you can already see that you can use the horizontal grid right here as your horizontal line test right here. Or for anyone who would like to learn a little bit more advanced ways to navigate around with this particular graphing utility, you can type the following. A equals, pick a number, for example, 5. Okay, just pick any number. And now Desmos will generate that as a slider. Now hit enter away. It's going to leave that A value here changeable as we slide the slider. And so now, right now, I set my A as a negative 1.8, or I can set my A at a different value. Okay, but now I'm going to type another line. X, Y equals A. This now will produce for me a horizontal line. And then we can change the color of this line by click and hold on that icon right there, and then click on that black color if you would like to use your black color for your line, and you can use a dotted line right here. Okay, and so now you can slide the slider here to start moving your horizontal line up and down. All right, to detect whether your function is a one-to-one function or not. Okay. All right, so if you are using a TI calculator, you can use a TI 83 or 84. They are going to be working. They are going to have the same functionality. To graph your function, f of x equals x to the fourth minus 4x cubed, then we can do that as the following. Now we click on the y equal button. I have had some work here from before, so I'm going to clear this out. But now to start here from scratch with this line right here. Now, so the graphing calculator here is capable of giving you up to 9, is capable of graphing 9 functions in the same graphing window for you. And we only need to pick one. So make your own choice. You can put your function that we're about to graph on y1 or y2 and y3. Now, this coloring feature is not available in the TI 83 or the earlier 84, but that should not affect your way to make it graph. Okay, so this is just optional enhancement that my version, the TI 84 plus CE, is offering. Okay, and so now I'm going to type x to the fourth. So this is the x key right here. So on my keypad, this key right here is the variable key. It has the x variable, the t variable. By default, it's going to go with the x variable. So we go x, okay, and now raise power. All right, raise to the power. And I purposely put this in the very classic view of the TI calculator. So that's how it looks, x to the, now I'm going to type fourth, so x to the fourth. Now I'm going to subtract, okay. I'm going to subtract, and now 4 times x cubed, so x, and raised to the power, so hat 3. That's how I can type it. Okay, and then of course I will have to leave that for you, any one of you using a TI calculator, to read your own manual to get fluent with how you operate with your calculator. And the same with any of you who are using a graphing utility other than Desmos or this TI calculator. Okay, and now once we've had the function enter, we don't need to hit save or anything like that. Just now hit graph. It will now pop out the graph. All right, and so now just like that, we don't have to worry about seeing the complete view of our graph inside of this small viewing window, because we can already see that now a little bit less convenient compared to the Desmos here. We cannot put in easily that a horizontal line like how I did, like how I do things with Desmos here. So just imagine that you put your finger to draw a line through this. The horizontal line is already, will cross the graph at 2 points right here. And so we can put another horizontal line here, and it crosses the graph at 2 points. So that's how we can use the horizontal line test here. Or right here in the x-axis, you can see that this horizontal line as the x-axis also goes through the graph at 2 points. Okay, but now primarily I would like to focus on how you can graph a function on the TI 84 on a TI calculator to have your result so that you can do your horizontal line test. So now after seeing that nature, now we have a firm answer. After seeing that nature about our graph like that, then this function, okay, now you can just simply make one answer over here. All right, so this function fails the horizontal line test. Okay, this function failed the horizontal line test. Okay, so that implies, now we can make our conclusion, f of x is not one-to-one. All right, So this function here is not one-to-one. So simply that method I showed, it's just, even though the function is not necessarily a function that we already know the graph, then use a graphing technology. Okay, and in case you use something advanced like this graphing, like this Desmos graphing utility, I also show right here in this example how you can navigate around to make your work run effectively like that. Okay, so now let's look at another one. So let's look at part B of the example. So we don't need to expect, so in my intention here, you don't need to expect that you are familiar with these functions. Okay, you don't need to expect that you are familiar with these functions. So I can just simply give you a rule. Let's say, how about g of f of x is given to be, so how about 2 to the x, 2 to the x. And again, nobody needs to worry whether you are familiar with a function like this. Just see that simply as a rule. It's a rule that takes on each input. The rule of this function says we raise 2 to the power being that given input. Okay, so 2 to the x is the rule of our function. Okay, and so now if you know the graph or you don't know the graph, that's why we have a graphing utility. Okay, and so now again with Desmos, let's type in f of x equals, so now 2 raised to the x power hat key x. Okay, and it instantly pulls out a graph. And then this feature is particularly good if this utility is particularly good if you're using this on a personal computer or on a Mac right here. So when you're on a computer, then you can scroll your mouse scrolling wheel to up, scroll it up, or scroll it down to zoom in and zoom it out, or to press on this to zoom in, or press on that to zoom out. Okay, and then you can click, hold, and drag like that to move the viewing window of your graph. Okay, and so now I want to create another command entry line right there. And now let's say I'm going to give a value. I'm going to set a value. A equals just any value, 3 for example, or 4. And that now creates for me a slider, just like how I did in the part A of the example. And now I type y equals a. That now will give me a horizontal line right here. All right, and then again we can adjust the color of the line by click and hold for a couple seconds, and then this menu will pop out. And then now I'm going to change this to a dotted line because that's just a line test that we're using. And now I'm going to slide the slider up and down. So this part down here is even way outside of the range of this function, so that doesn't count. We're going to slide that up. Okay, but now anywhere I'm moving my line up and down right here, the graphing utility, the graph shown here is indicating that the graph, the line, the horizontal line itself only crosses the graph at 1 point. Only crosses the graph at 1 point. Okay. All right, and now for anyone who would like to graph the function f of x equals 2 to the x with a TI calculator, I use TI-84 plus CE, but TI-83 and 84 will all work the same. The standard TI-84 will also work the same. So we want to go first, y equals, that's for us to input the function. So now the function is 2 to the x, so 2 raised to power hat key to the x variable is this key right here. So 2 to the x. And now I hit graph. And that is the function, that is the graph for our function 2 to the x. Okay, we don't have to have any advanced understanding about this function yet, but now we simply just look at this graph and be ready to use our horizontal line test to decide whether our function is our function 2 to the x is a one-to-one function or not. Okay, and so in that way, now I'm ready to make my final conclusion. This function seems that at least within what we can do right there, within what we can view, it passes, this function passes the horizontal line test. So f of x, because anywhere we place the horizontal line test, right, the line only crossed the graph at 1 point. So now I'm saying that f of x passes or passed the horizontal line test. All right. So now that in that way, I can conclude that f of x is 1 to 1. All right, and f of x is 1 to 1 for this particular problem. All right, and so now, before I'm leaving this example, now allow me to show an FYT problem. And again, my only intention is for you to use and get comfortable with using your graphing utility again, but you are not required to be the master of any of these functions that I gave in this particular example. Okay, so let's look at how about as an FYT. All right, so now let's look at f of x defined as absolute value of x. Okay, and so if you are using technology, most of the time we type ABS as the command and then x, close the parentheses for your technology like that. Okay, that's for a lot of programs, including your TI calculator. We'll use this command right here as absolute value. All right, so now go ahead and pause the video, okay, and then get your functions graphed, and then decide whether this function is 1 to 1 or not 1 to 1. All right, so now I assume you have already pulled out your graphing utility and had this function graphed. I would say that this function f of x is not 1 to 1. All right, that's the conclusion.